So, say a couple of things about the next homework, which this is one of my favorite fun homeworks. I took a problem off of each one, so I'll say that. Okay, so basically what I want you to do in this homework is get out your dissecting tools and figure out what the Galois groups of some of these polynomials are. First, we consider the polynomial x to the fifth minus 3. Let f be the field obtained by adjoining one of the complex roots. And by complex, remember, that also includes reals, right? Any real number is complex. Of the above polynomial to q. So I don't care which one you use. Find the degree of f over q and show that this extension is not Galois. Now consider this other polynomial, x to the fourth plus x cubed plus x squared plus x plus 1. Show that this is irreducible over f. It is not too difficult to show that it's irreducible over q, but I also want it to be irreducible over f, which is this larger field that you got by obtaining one of these roots. There's an earlier homework problem that might make this. You can kind of do this the hard way, I think, and get on your bulldozer and just kind of drive. Or there's a homework problem that might help it be a little bit easier. And number C, if f bar is the field obtained by adjoining all of the roots of f of x to q, find the Galois group of f bar over q. And hint, this must be a transitive subgroup. That's 5. By the way, I took off the last part because I just got my experience of doing it didn't really do that much. But just for giggles, every one of these polynomials I give you, you can solve by radicals. There's a formula to find all the roots in terms of square roots, nth roots, whatever you like. See if you can do that, just for fun. Number 2, consider the field f obtained by joining all the roots of the polynomial f of x is x to the 6 minus 3x cubed plus 1 to the rational numbers. Number A, show that complex conjugation is a non-trivial automorphism of this field. Don't try to read too much into this. This actually isn't too difficult problem. If A is a real root of this polynomial, show that the map induced by alpha goes to alpha inverse gives rise to an automorphism of Q of alpha. Show that the degree of this splitting field, f over q, is 12, and find out what the Galois group is of f over q. And finally, consider the polynomial f of x is x to the 6 minus x cubed plus 1. So it's just a slight variant on the previous one, I guess. And let f be the splitting field of f over q. Show that there's an intermediate field E between q and the splitting field of degree 2 over q. And then find the Galois group of f over q and find all the intermediate fields, right? Actually, there's not a lot of them. I think that you will find the quadratic intermediate field not too difficult to find, but there's another one, another intermediate field that you might have to think about a little bit too. You should know from Galois theory, if you figure out what the Galois group is, that field exists, but figuring out how to present it might require a little bit of thought. Okay, any questions on that? All right, so let us kind of pick up where we left off here. One of the things that we had in this theorem is that if you have an irreducible polynomial of degree n, then the Galois group of that polynomial must be a transitive subgroup of Sn. So I'm going to do a lot of Galois groups over Q. Okay, so So if you have the symmetric group on two elements, there's only one transitive subgroup, and that's the whole thing. Because the alternating group is the identity, right? So. You get S3 and H right here. Transitive subgroups of n equals 4. Notice you should probably prove to yourself that both Sn and An are transitive subgroups of Sn for n greater than or equal to 3. The cyclic group of order 4 is also transitive. We discussed this a little bit last time. And so actually one of the things that you might observe is in Sn, if you contain an n cycle, it has to be transitive, right? Because without loss of generality, you've got the cycle 1 through n. And so just taking appropriate power can take 1 to anything. And since you can permute the cycle, it works for any of them. But there are several Z2 subgroups of this, and the one that's transitive particular client 4 group is the one that's transitive, right? Which is kind of a weird thing. By name, any other transitive subgroups of S5? C5 and D5. There you go. Right. Let's just kind of follow the lead here. I apologize for this. These are analogous. Cyclic order 5, D5. There is one more. It's commonly called. This is the Frobenius group, 20 elements. Generated by a 5 cycle and a 4 cycle, a particular 5 cycle and 4 cycle. In fact, you can generate this by, or you can generate one of the copies by. That's one of these things. This is a subgroup of order 20 and S5. And of course, when I show you that one of the generators is 5 cycle, then you're good to go, right? In fact, all you have to do is really show that there is a subgroup of order 20 in this, and any subgroup of S5 of order 20 has to contain a 5 cycle. And so would a subgroup of order 30 or 40. Unfortunately, S5 doesn't have either one of those, right? There's no subgroup for 30 or 40 in S5. You will forgive me for not listing that. There are 16 of them. We're in 6. Right, there's 16 up to isomorphism. There's 7 here. And I bet you might be able to figure those out if you thought about that, because 7's prime is easier. Transitive subgroups of this are getting out of hand pretty quickly. Up to isomorphism, there's 50 transitive subgroups. That's 8. And for this one, it's, what is it, 301? Yeah. No, my bad, no, that's not. That's not a little thing. Right. So there's lots of transitive subgroups of S12, as you can see. There's a huge number of them. So what I'm gonna do now is I'm gonna take kind of a little excursion into what I'm gonna say at first sort of works in general, but I'm going to apply what I'm gonna talk about next to small degree, small polynomials of small degree over the rational numbers. So definition, let's say 853. Let's let f of x be in k of x where the characteristic is not 2. And n is equal to degree of f of x. Suppose that f has n distinct roots in some splitting field. F of x has n distinct roots. Splitting field of it. So in particular, if f of x is irreducible and the characteristic is 0, then this will always be satisfied. Then we define delta be this product Ri minus Rj, where R1, R2, Rm are roots of f of x. So you look at this product here, and it's just, so for example, if n is 3, it's a 3-degree polynomial, it's R1 minus R2, R1 minus R3, R2 minus R3. So it's the product of all the difference of the roots. And perhaps at this point, you see why we want the roots to be distinct, because if they're not, then this turns out to be 0. We define the discriminant of f to be so we define the discriminant to be the square of this product of the difference in the roots.
Is that related by any way to the discriminant, the general formula for a quadratic equation?
Well, let's see. All right, so for example, if you have, all right, so let's assume irreducible. Then what are your roots? A negative a plus or minus square root of a squared minus 4b over 2. And I'm going to do this assumption that the characteristic is not 2. Or 2 is negative a minus square root of a squared minus 4b. Right. So in this case, your delta, I mean, there's only one thing to do. It's just the difference between these two. Right. So it's going to be R1 minus R2. So it's going to be Correct. And it's exactly the thing that goes up to the radical, so that's right. So that's the connection to this word that you've heard before, when you were doing quadratic equations. And this goes deeper than this. Proposition, or I should say, more generally, proposition 854. If D is always in K, and as it turns out, D is always in K, and delta, that is the square root of this, is in K, if and only if the Galois group of F can be realized as a subgroup of AN. That is to say, and let me clarify this. Where F is splitting of F over K. So this is kind of nifty. So let's take this back to this example here, right? So what does it say? This says, okay, my discriminant here, which is this thing, it's pretty clear from this quadratic case that this is an element of the field, right? Because this is a squared minus 4b, and a and b are in the field, so a squared minus 4b, right? Now, there's your square root of the discriminant, right? What happens if this is in the field? So in other words, what happens if a squared minus 4b itself is a square? When you take the square root of this, this is negative a plus another rational number. So your roots are already in there, right? So this theorem tells me that the Galois group of that polynomial should be a subgroup of A2, right? And A2 is the identity, right? So in other words, what that means is a splitting field. If the thing that goes under the radical in the quadratic case is actually square in the field, that means that the Galois group is trivial, which means it's a polynomial already split in the rational numbers. If it's not, then this is not a subgroup of AN, but it's a subgroup of A2, and your only choice is not A2, S2, and so you get the non-trivial two roots here, right? But this is kind of nifty in that it persists in general. Let me give you an example. You should try to, just for fun, because I want to get through a lot of examples, you should try to see if you can verify this, get your hands dirty and do this. And I'm going to use this example later. So for a cubic polynomial, x cubed so if I have a cubic polynomial, the discriminant is given by now the discriminant, of course, is the thing that should be in the field. This is a squared b squared minus 4b cubed minus 4a cubed c minus 27c squared So, by the way, that's a fun one also. Well, depends on what you like, what you consider fun to be, I guess. But, I certainly, big, bit of a masochist. I would think that's, kind of fun. How do you figure this out? Well, see if you can do this computation. So this does have 3 roots somewhere, right? Put this back together and see what you can come up with, see if you can do it. Because, this is just, so this thing right here should be, R1 minus R2 squared, R1 minus R3 squared, R2 minus R3 squared, and there's enough information here to give you this. So for example, minus 1. Let's go through this. In this case, A is 1, B is -2, and C is -1, right? Then D is equal to, let's see, that's going to be a 4, right? That's going to be a plus 4, right? And that should be negative for sure. That's going to be 27 times 27. And then 18 ABC, that's going to be positive, so that's going to be plus 36. Which doesn't look right.
Or B for Q.
Did I forget one?
Yeah.
I forgot one. That's what my problem is. I went straight to, okay, so, and this one is going to be, plus 32, isn't it?
Yep.
There's the difference right there. So that's going to be, 17 and 32 is 49. Okay. Now notice that 49 is of course a square in Q. So far I really haven't specified the base field here. Now if you, so this basically tells you all that you need to know, right? Let me ask you this. I have a cubic. So if I have a cubic that's irreducible, suppose f of x is an irreducible cubic, let's say over Q, then the Galois group of F, and remember that's the Galois group, splitting field is either blank or blank C3 or S3. It has to be Z3 or S3 because it has to be a transitive subgroup of S3. There's only 2 of those. Now, for this particular one, it turned out that the square, or the discriminant was actually a square in the field, which means that in this case, the Galois group has to be a subgroup of this. And of course, this is the only one that's a subgroup of this. So in this case, the Galois group. So for our polynomial, then C3. Yes, absolutely. I also know, immediately that this polynomial, see, I didn't even take any derivatives or anything yet. This polynomial has to have three real roots. Explain to me why.
Conjugation doesn't happen, there's some polymorphism.
That's right. If this thing had, let's suppose that this polynomial here had a pair of non-real conjugate roots, that would mean that the splitting field would have to have that order two automorphism, and two does not divide that, right? So there you go. And in fact, I'm going to generalize that observation after a bit.
Oh, but it does divide six, but that it's in where for the Galois root to be S3, you have to be able to send any root to any root.
Yeah, that's right, that's right. Well, so what happens, so S3 as opposed to Z3, of course, in any case, if you've got an irreducible cubic, it's got three roots, right? We're assuming three distinct roots, well, characteristic zero. And so given any pair of roots, I don't care which, there is an automorphism that sends one to the other, right? But in S3, you can do any permutation, right? So there's more ways, if you will, to permute the roots, if the Galois group was S3. So really, here's the deal. If you take that formula for a discriminant, then all you gotta do is compute it. And then look at what you get. If the D is a square in your base field, then the Galois group is Z3. And of course, I'm assuming the polynomials are reducible. And if it's not a square in your base field, then it's S3, end of story. I'm gonna up the voltage a little bit and show you how to deal with quartics. So the cubic is so if your goal in life is to find the Galois group, cubics, we can do that. How about quartics? Well, let's take a look at that. So I'm going to assume that K is a field characteristic not two again. F is an irreducible polynomial of degree 4 with distinct roots. So here's my setup. F, well, the characteristic of K is not 2. F of X is an irreducible quartic. With distinct roots in its splitting field. And let's see what else that say. Okay. So what you did Galois group of the polynomial, that is Galois group of the splitting field over the base field. Okay. Now, S4 has 5 transitive subgroups. They are S4, A4, Z4, D4, and B. I'm going to call it B. It's just notation. E. 1. And I'm gonna go through something here that's gonna demonstrate this. So here's kind of a. Now, how many of you have seen the quadratic formula before? Please, hurry up and raise your hands. Just out of curiosity, how many of you have seen the cubic formula?
Yes,
Third.
remember it?
Right, yeah, remembering is another thing. How many of you seen the quartic formula? Oh my gosh, that is death on a hot plate, right? I mean, because what do you have to do if you look at most algorithms for doing a quartic? I've actually given several math club talks on how to sort of from ground zero solve a cubic equation, which is kind of a fun thing to do. I have not had the courage yet to try to figure out if I can jam a quartic equation into a 50-minute talk. Because what you do is you first evaluate this associated cubic. So you've got to do the cubic first. It's just a nightmare. And why do you have to do this? Well, the cubic is bad, right? But then to do a quartic, you usually do a cubic and then you do something else. And why do you have to go through this? Well, this might give you a hint. To find out what goes on in a quartic, I don't know much, but I know that whatever this quartic irreducible polynomial, its Galois group has to be isomorphic to one of these 5 groups. And I am going to key on this group here as kind of a step ladder to help me figure out, what the big picture is. So let me give you the following lemma. 8.56. Using previous notation, suppose that Ri denotes the roots of f in f. Suppose Ri are the roots of f in its split field. Let's let alpha beta gamma. So many special elements here. This is going to be R1 plus R2, R3, R1, R2. Beta is going to be R1, R3. This one R1, I'm sorry, R2, R3, R1. Oh, I guess I should have done this way. That would make more sense. There we go. 1, 2, 3, 4. Anybody know what's special about these? Or why we want to pick this?
I mean, they're the same as cycles.
That's right. So if you look at this root, for example, here, right? What happens when I act on it by this element? Right? It's fixed, right? Because what that first element in that B group does, first non-identity element, is it essentially swaps roots 1 and 2 and 3 and 4, so it's fixed, right? So these are kind of set up with these elements here that do these little swaps. Okay. Right. So let's make more room for this little lemma here. under Galois correspondence, then the field K adjoined with alpha, beta, gamma. So the smallest field that contains those three elements that we have here corresponds to the normal subgroup D intersect G. So in particular, K, alpha, beta, gamma is Galois over K with Galois groups. G mod D intersect G. Okay, so this is actually not too difficult to show, actually. In fact, if we think of this, just to make things easier, so notice that, of course, the key bit here is that this thing right here is normal. And in fact, this is an abelian group, and it's a normal subgroup of S4, right? And so this thing right here makes sense. This has to be B intersect G has to be normal in G, and right. And so by the Galois correspondence, this should be the Galois group. So this is Galois. So it's effectively a splitting field, an intermediate, perhaps an intermediate splitting field. So how do we leverage this? So I think we've got enough here. Now here is, like I said, if you've ever seen the quartic formula, you see somewhere along the way they give you something that they call the resolvent cubic, and you have to work something out with that before you get the entire formula. Proposition. Proposition 857. Let K be a field and F and x to the 4 plus 8x cubed plus bx squared cx plus d. So we have this polynomial right here. The resolvent cubic we're going to define to be cubic is R of x, which is defining this to be x cubed minus bx squared plus AC minus 4D x minus this crazy constant term minus A squared B plus 4BD minus C squared And it turns out, where does this, I mean, this really looks like, you know, Gandalf walked in and waved his staff or something. But what this really is this is X minus alpha, X minus beta, X minus gamma. That's what this is. If you multiply this out and write down what alpha and beta and gamma are, you know, those R1, R2, all that business right there, you will in fact get this. Now notice that, right, notice that these elements are permuted by V, right? I mean, for example, the alpha element is fixed by the first thing, but the other elements just move it around to different ones of these roots, right? So here is kind of, and of course this is, it's probably not so clear when I write it this way that it's in KX, but it's very clear when I write it this way, it's in KX. Now, here is kind of the big theorem. So we've got our irreducible polynomial, our quartic. It's got roots R1, R2, R3, R4. We build these alphas basically to set up this resolvable cubic. Notice that what happens is the action of the Klein-Porter group, that V group on this, just permutes these roots, so it fixes all this. And here is kind of the big final picture for quartics. Let K be a field and F an irreducible quartic. Field and F an irreducible quartic with distinct roots in a splitting field. Irreducible quartic with distinct roots in a splitting field. And we'll say G Galois group of this polynomial. Notice it's a subgroup of S4. It's a transitive subgroup of S4, as a matter of fact. Let alpha, beta, gamma be the roots of the resultant cubic. The roots of the resultant cubic R of X. So these are exactly alpha, beta, gamma, exactly the things that, so this is R1, R2 plus R3, R4, et cetera, where these are eyes of the roots of the quartic. And let M be let M be the degree of this extension over the base field K. Right? So we have the following. Number one, Uh, M equals 6, right? Suppose that this extension is true 6. This is true if and only if the Galois group is isomorphic to S4. Because essentially what that means is you've got to jump the full 24. So you go 6 here and another degree 4 extension to get to the entire splitting field of the quartic, right? Because the size of the V group, that Z2, Z2 is 4. 2. M equals 3. Anybody want to guess? Okay, good. Right, you don't have to go half as far, so to speak. 3. What if in this 1? What, so that means alpha, beta, and gamma are already down in K. And what's the Galois group? Nope, nope. It's V. It's of order 4. But it's actually C2, Z2.
Oh, I said before, but.
Uh, hmm. Well, there's 5 transitive subgroups. That's 4. That's got S4 covered, A4. This has got D covered. There's 2 more. There's cyclic of order 4, and there's the dihedral. And they're both subsumed in this case. If and only if G is isomorphic to Z4 or D4. And you feel the tears welling up because, oh my gosh, how do you tell? How do you tell which one? But don't cry, I can tell you. In this case, G is isomorphic D4. In this case, G is isomorphic D4 if and only if F is irreducible over K alpha beta. So that's the last stepping stone that you need, right? So take your polynomial F that started this whole excursion here. Take the polynomial F and look at it over this field here, right? Of course, this field is going to be quadratic over K in this case, right? So it'll be a quadratic extension. Take whatever F is, if it reduces over this, then you get Z4. And if it's irreducible, you get D4. So I don't have time to work these examples, but we'll pick this up next time. And then I will tell you a very sad story. But I'm going to tell you the examples I'm going to go over next time. So I'll give you time to, cogitate before then. Let me give you these polynomials here. And I've set these up to work out nicely, but you can play around with any kind of complicated thing you want. Now, for instance, x to the 4 minus 10x squared plus 4. And x to the 4 minus 2. By the way, before we get too deep into this, before you think too much about it, I guess, and let's say that these are over the rationals. Okay, let's just do this. can you explain to me why these are irreducible? Eisenstein works on which ones?
First,
He's right. The Eisenstein criteria works for this one and this one. Why doesn't it work here? Yeah, the pesky 4, it's got too many powers of 2 in it. This one's irreducible as well. See if you can figure out why that's true. And all 3 of these have different Galois groups, actually. And we'll see if we can get to the bottom of this next time. Any questions? Let me remind you that Jared is actually giving a macro talk that I think might be interesting to a lot of you because it's kind of at the roots of mathematics, sort of getting back to the basics, like REM on the Monster album. And anyway, so it should be fun, philosophically and you know, logically what goes on with math. So hopefully y'all can be there. Other than that, y'all have a good weekend and we'll see you on Monday.